All right. Hello. This is truly going to be a question and answer session. I have nothing prepared. In fact, I should be entering grades instead of doing this, but here I am. I might be distracted as I do enter some grades, but you have the opportunity to ask questions, and I can try to re-explain some things. If this is the first time Listen, if this is the first time you've looked at science this weekend, I'm not just close out. I'm not dealing with that. Okay? This is for people who have studied already, who have hit something that they might have forgotten or hit something that they need help with going through an old worksheet. This is not a come listen to me and I reteach everything to you. I'm not doing that. I have other stuff I need to do, and you should have been studying all weekend instead. So if you have actual questions, you can put them in chat. If you want to just hang out and talk to each other, you can do that on your phones. You don't need to do that here. So if you want to use this time, I'm here. If you don't, then I will leave. That's basically what it comes down to. All right, first question. What do you mean when you say voltage is potential difference? It's literally just another name for it. Okay? Voltage is potential difference. That's what it is. It's another name. Could you explain what happens to the voltage and current when you add resistor to a series and parallel circuits respectively? What do you mean? What does it mean, Sod? It's a name. Voltage is potential difference. That's what voltage is. So potential difference is the real name. It's what it is, and voltage is the name we give it. That's all you need to know. That's all you need to know. What happens to the voltage and current when you add resistors to a series and parallel circuits, respectively? Voltage and current in a series. So when you're looking at voltage, it deals with resistance. Okay, so when you're looking at voltage, you're dealing with resistance. The same current is going through no matter what. So when you're looking at a series, series circuit. So let's look real quick. Let's get a picture of a series circuit. Alright, Aquino, that's a real easy one. I'll take an aside. Whether force is present during freefall, literally gravity. That's it. Done. Gravity. Done. That's all you need. If you're in freefall, you're in gravity. That's it. Alright. Here is our series. And then let's get a parallel. Trying to find a good parallel circuit. There's not very many great ones. This will work. Nope, not gonna work. Alright, maybe I'll try mine. Okay, so we are looking at what happens to a voltage and current when you add resistors to a series and parallel circuit, respectively. Okay, so when we're looking at a series circuit, okay, so here's our series circuit. Okay, we have our voltage, our power source here, our battery, our cell. Okay, and the current leaves and goes up, or the current goes here, then it goes here, it hits this resistor, it goes here, goes down, hits this resistor, goes here, goes here, hits this resistor, goes here, goes up to the other side of the battery, so on and so forth. So you get a nice circuit here. You're going up from the power source, around the wires, interacting with the resistors on the way, and then you come in and you enter the other side of the battery. Cool, we have our current flowing. Okay, now why is this important in a series circuit? Well, the current, current is equal to I, that's our variable, and it is amperes. How do you spell amperes? Is it I think it's one R. Amperes. So our current is our variable I, and it's in amperes. This is the unit. Okay? And so when you're in a series circuit, you're looking at how the current flows. So our current goes up, over, around, so on and so forth. There are no other ways for that current to go. It can only leave this battery, and it can only go across in this this route. Now, if you cut the route, then you no longer have a circuit, okay? Because the current cannot complete the circuit. So therefore, you have an open switch or something along those lines. But in a series circuit, your current doesn't change because it can't go anywhere, okay? So your current can't go anywhere. That's what you're looking at for a series. Now, your voltage, as you go across, the more resistors you add, the more light bulbs you add, the more stuff that the current has to go through, the less voltage they get. Okay? So there's something called voltage drop, and there's mathematical ways to calculate that, but we don't have to do that. Okay? And so when you're looking at your series, your voltage, every time you add a new resistor or you add a new light bulb or something like that, voltage drops when there's more stuff. It's a good way to put it. Voltage drops when there's more stuff. When you have more light bulbs on there, you have a lower voltage. And that lower voltage results in your light bulbs being dimmer. Okay, it's not as bright. The more light bulbs you have in series, the more it has to share the voltage. If it's sharing the voltage determines how bright it is. So if you're sharing the voltage, then it's less bright. Okay, and that's a series circuit. So the series circuit, your current stays the same. Stays the same. Okay, and then your voltage, when you add more stuff, it drops. Okay, that's what we're looking at. So when we have a parallel parallel circuit, so we have our battery here, we go across, let's say we have a resistor here, and we're going, this is currently a series. What makes it a parallel is if you add a branch. Okay, now, look at the current here. We leave, we go over, we interact with our resistor, we go over, we go down, interact with our resistor, we go over, and we go up. Okay, so we have one loop here, but the current does not have to go down. It can go over this way, down this way, over this way, and then keep going. Okay, so what happens to your current over here? The current is lower. Okay, your current's lower. But here, this resistor, so R1, and this resistor R2, we'll call this one R3. Okay, R1 and R2 have the same voltage. So if you wire something in a parallel circuit and you want the light bulbs to be the same brightness and you want it to be brighter, you put them here. Now, if they were in series, like these light bulbs, they're still the same brightness, but they dim. For every light bulb you put on a series circuit, it gets dimmer. Both of them get dimmer. If you can put as many of these branches as you want in here, okay? the brightness of the bulbs will stay the same. It's not going to dim. Okay, so it's going to stay the same as you go, as you add more and more parallel branches. Okay, so your current gets lower. I like to think of current as, well, it's moving electrons. So I like to think of the electrons as little ants. You know, you get your little ants, boop, 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 boop. And they're walking, they're walking, they're walking, they're walking, they're walking, they're coming here. Oh gosh, it's a fork in the road. Well, some can go down and some can go across. So therefore, since some ants go down, some electrons go down, some go across, the amount of electrons that come through, aka your current, is lower. Okay, so your current lowers, but your voltage stays the same. Okay, that's different than the series. Okay, and we're going to call it there. Let me scroll up in chat. And let's see. Okay, so that's what is it. Another thing you need to know about your series and parallel, you need to know the advantages and the disadvantages. So here's two advantages. Advantages of a parallel. Okay, the voltage doesn't drop. So you can have bright bulbs, as many as you want, all from the same power source. Okay, so your voltage doesn't drop. Now your current does drop. Okay, so eventually you won't have enough current. Okay, but the thing is, also with parallel, remember, because we're splitting our current here, okay, because our current goes this way or goes across, you can get rid of this entirely, have an open switch here, okay, so an open switch there, and this will no longer work. But since it split the electrons, this light bulb still turns on. Whereas if you lose out on this light bulb up here in the series, these also lose out because you broke the line. The electrons come up, they got nowhere to go. Okay, therefore they never get to these other two light bulbs. Whereas here, they come up, you break the line, no problem. They're still going over here to this light bulb. They're still going to light up those things. So in a parallel circuit, you can lose one of your branches and the other branches will function just as well. In a series, if you lose a light bulb, you're done. It's out. You got to replace the whole bulb. You got to remake the whole circuit. This is how they used to make Christmas lights, and it was so annoying. You would decorate your whole house, you'd plug it in, and nothing would work because one of those bulbs was working, and you had to go through with your little tester and test and replace the bulb that was working, and all of a sudden all your bushes would then light up. They have since changed that, and they now make Christmas lights in parallel for that whole reason. The parallel circuit, that one of the bulbs can go out, and it won't make a difference. The entire Christmas tree will still be lit up. Okay, that was so annoying growing up with that. You can ask your parents about that. Okay, alright, so that's series and parallel. Remember, there's math. Okay, for series you have your resistance, you add all the resistors up, and that's your total resistance. For parallel, remember, it's 1 over the resistance, you add them up, you take the reciprocal, that's your resistance, so on and so forth. Those are in your notes. You can go look at them if you forgot. Okay. Alright, what's the difference between open and closed? Alright, we're going to call this here. I'm erasing this. Real quick, put in your, before I scroll back up and look at the next question, are we good with these two things? Advantage of series? Yeah, the advantage of series is your current doesn't drop, dude. It's a good thing. Okay, your current stays the same through all the stuff. Alright, if when the bulb breaks on one side, does it dim on the other side? In a parallel circuit, no. No, this bulb has no care in the world what this bulb does. Literally doesn't care. This bulb can be on, shining, it can be broken, it can be stolen, it doesn't matter. This bulb is going to shine on, it's going to do its thing. Okay, so it does not matter. Alright. And next question. We're scrolling back up. Alright. Alright. Can you explain what surface area is? Sure. Surface area? Alright, look. Well, it's just like area, right? So draw a square. Draw a bigger square. Okay. You have your area here. Okay, so area is what's within the square. Okay, so this is all the area. All within the square. Now the area within this square is obviously bigger. Okay, so this obviously has more inside of it. This is obviously a bigger area. Now think about it. If these were falling, now this is a cube, right? So if this is a cube, okay, cube it, so on and so forth, okay? So we got our cubes, right? Okay, now each side is the same size. It has the same surface area on each face of the cube, okay? So if these are falling down, okay, and then say you have air here, right? Woo! Our little air. Obviously air doesn't look like this, but stay with me, okay? You're going to hit more of the air with this giant thing, right? It's going to fall down. Look, we're going to hit all this air, all of it. All of it's hit. Whereas this one is only going to hit a little bit of the air. Right? Make sense? So the more surface area you have, the more air resistance you're going to have. That's why you want a parachute, right? You want a really big parachute, and it's going to give you more air resistance, so you have a smaller terminal velocity, and you're better off. You don't die when you jump out of a plane. Okay, easy way to figure this out. Take your hand, run it through the air. You can barely feel anything. Turn it this way, run it through the air. Okay, you can feel you're making a wind, whereas here you can't really. Okay, more surface area. The side of your palm is larger than the tips of your fingers. So if you're just running the tips of your fingers through your air, it's no big deal. You run your palm through the air, you can actually feel the air. You feel the air resistance. You're making a kind of a little wind, okay, because you have a larger surface area. Okay, so that's surface area. Okay. Does air resistance slow you down? Absolutely. Slow you down? Well, that's relative. Okay, because look. Okay, let's see. We have our dot and our dot. Okay, so this is cube 1. This is cube 2. Does it slow you down? Probably not. Does it have a smaller acceleration? Absolutely. Okay, so we have our force grav pulling this down, and since this is a small surface area, we have our air resistance going down. So here we have our force grav. Larger surface area means it's a larger air resistance, which means this net force is a small downward arrow, where this net force is a larger downward arrow. Okay, why is net force important? Because F equals ma. Now, obviously, this has more mass, okay, than this one. So, if you dropped them, okay, depending on the surface area, depends on the air resistance. More surface area is more air resistance, okay? So if these somehow had the same mass, so let's just say these have the same mass, okay? So this is mass of 5, this is mass of 5, just go with it, okay? Then our acceleration is what we care about. The acceleration is equal to our force over our mass. Okay, if they're both over 5, that means this guy with the smaller net force will have a smaller acceleration. That smaller acceleration means you don't get as fast as quickly. So, does it slow you down? Technically, no, but for all intents and purposes for you, you fall at a slower rate. Okay, you're still falling, but you fall at a slower rate. Okay, you're not accelerating as much. Okay, so that right there is Newton's second law. F equals ma. Boom. Okay, we got to be able to identify all 3 laws. Well, this right here is Newton's second. We got it. Newton's second law. Woo-wee. The smaller net force, the smaller acceleration. That's what you're going with. There you go. They're related. Look at us. Algebra. Okay. Scrolling back up. Alright, what's the difference between an open and closed system? Now, open and closed system has different definitions, so it can be a little confusing. The definition we are going with for an open and closed system is our open system deals with either energy being added, energy being taken away, so on and so forth. The open system, what you need to think of for open system is, do you have the same exact amount of energy that you started and ended with? If so, it's a closed system. If you don't, if you added or took away, then you can call it an open system. Okay, now technically once you get to high school and college, you may need a different definition, but for right now, that's the definition we're going to go with. Okay, you look at the types of energy. Okay, and if it is technically, so let's see, right? So we have a diver. Okay, and he's diving off a cliff. Very brave. And he's going into the water below. Okay, at this point, right here, okay, he has 100% potential energy. Okay, 100% potential energy. What that means is all of his energy, he's standing up here at the top, okay, all of the energy that we care about right now is all potential. Once he drops, and he is literally about to land, okay? Okay, he's diving in, okay? At this point, right before he hits the water, he has 100% kinetic energy. Okay, so we're looking at our energy transformation. We started with potential energy, it then moves into kinetic energy, but the total energy is always going to be your potential energy plus your kinetic energy plus whatever else energy you're dealing with. But in this case, we only have 2, so that's what we're looking at. Okay, so your total energy is going to be that. So your total energy doesn't change. This is 100% at the top, and this is 100% at the bottom. Well, then your total energy never changes, because while these change, your total energy stays the same. So that's what we're looking at. If the total energy stays the same the entire time, then we can call that a closed system. But we're smart people. If it tells us that there's air resistance as he goes down, okay, so he jumps into the water, but this time there's air resistance. Okay, that means he got a little friction. Okay, that means up here we have 100% potential energy. But down here we have our kinetic energy, but we lost some thermal energy along the way. So our thermal energy, it converted into thermal energy, and it dissipated as heat. So therefore, this kinetic energy is no longer equal to this potential energy. So here, these two are equal. PE is equal to KE. If you need to find your kinetic energy down here, you can find your potential energy, and they're literally equal. Okay, this is no air resistance or friction. Okay, so this is no friction. Whereas here, we have friction, and our potential energy at the top is not equal to our kinetic energy. Okay, because some of that potential energy switched into thermal energy. So if you looked at total energy for this one, our total energy is equal to our potential energy plus our kinetic energy plus our thermal energy, right? Because that thermal energy didn't come from nothing. It had some of this potential energy transformed into this thermal energy. So our total energy stays the same. Total energy never changes. Okay, your total energy, the law of conservation of energy says energy cannot be created nor destroyed, so therefore it stays the same. Okay, but we can kind of get away with calling this an open system because our potential energy is not equal to our kinetic. Whereas here, we can call this a closed system because it is. Your total energy never is different. Your total energy in the beginning and your total energy at the end is always the same. It's just what did it transform into. That's what you're looking at. Okay, so what are the forces present during free fall, Aquino? Well, that's just gravity. Only gravity. Okay. All right. There's a lot of chat. Oh, God. Oh, God. All right, I'm just going to go through chat. So, terminal velocity. So, Nathaniel, terminal velocity have to do with acceleration, right? I don't know what that means. What's the Aquino, what's the difference between an open and closed? I just said that. Okay, moving on. Can you explain time and distance graph at a constant speed? Absolutely. Time and distance graph. Okay, so here we go. Look at this. We're about to get fancy. Look at this backgrounds. Oh my god. Oh my god, he's a magic man. He's a magic man. Oh, we're getting crazy. Alright. So, we have our distance. We have our time. Okay, and over here, obviously, we're going to have our secondary graph, where this is obviously velocity. Well, if I could write, it would be velocity. And this is time. Okay, so we have our two motion graphs. We have distance and we have velocity. Okay, so as we go through here, we are looking at our two graphs. So distance, here we go. Think of this. So 0 distance. Okay, if you are at your house, so here we go. Little house on the prairie. You guys are too young for that show. Okay, and we've got Bob. Hi, Bob. Okay, so here's Bob. Okay, Bob is walking this way. Okay, as Bob walks this way, he ends up over here. Wow, he moved. Mad lad. Okay, he walks this way. Okay, so Bob has moved away from the house. So here's our house, okay? This is home. This is what we care about. This is distance 0. Okay, now Bob started at home. So he started at 0. Okay, he then went this way, and let's just say this is, let's say, 1, 2, 3, 4, 5, 6, 7, 8. So he's roughly at 7.5. Okay, so he started at 0. Okay, and he ended at, let's say, 7. So here we go. 1, 2, 3, 4, 5, 6, 7. Okay, so he started here, and he ended all the way up here. Now, how long did it take him to go? Well, if you went 7 meters, let's just say it took, let's just come over here. Sure, took this much time. So as time was going, he walked from 0 to 7 meters this way. Okay? Now, if he stays there, okay, and he doesn't move, our time keeps going. but our distance stays the same. So he's at 7 this entire time. So as time goes, he's at 7. Okay? And then he decides, you know what? I forgot to pet my dog. I need to go back and pet my dog. So he goes back all the way to home. Okay, and you can show that on a graph. Except this time he's going to run. He's like, oh my god, I can't believe I forgot to pet my dog. I have to get back there right now. Okay, have to get back there right now. Okay, so as he goes, he starts running. Like, oh my god, my dog's gonna hate me. So he runs all the way home. Okay, so now he's at distance 0. He's back at home. Okay, and here it only took him, so here it was 0 to 7. Okay, and it took him, let's say 1, 2, 3, 4, 5 seconds. Okay, so this was 5 seconds. And here it took him 1, 2, 3 seconds. He's a fast dude. Okay, fast dude. Yeah, time can be in seconds, can be in minutes, can be in hours. It doesn't matter what your unit is. Okay, as long as it's a unit of time. So here and here. So he traveled the same distance. He went away from home 7, and then he went back home 7. So away from home, and then back to home. Remember, 0 is home, so away and back. Now, using this, you can figure out his velocity. Okay, remember, velocity is nothing more than distance over time. So velocity is distance over time. Okay? So if he did his first velocity, if he went from 0 to 7, that's a distance of 7, and it took him 5 seconds. Okay? So this is his first velocity. We'll call it V1. Okay? Now V2 was, well, let's see, what's 7 divided by 5? We'll say 1.4. And this was meters per second. Okay, because we said it was 7 meters, 5 seconds, meters per second. Okay, right? 7 meters, 5 seconds. These are divided by each other, meters over seconds. Good. Our velocity 2 was from 7 to 0. So again, that's 7 meters. But this time it was in 3 seconds. So his velocity 2 is 2.33 meters per second. So he was moving faster in the second one, and you can see that based on this line is steeper. Okay, this one's a little bit more drawn out. This one is steeper. Now, when we talk about drawn out and steeper for our graphs, right, that's called our slope. So when we're looking at velocity, it's distance over time. Well, that is the slope of the graph. Boom. The slope of the graph. Okay. Now remember, this section right here, he traveled 0 distance. So it's 0 divided by whatever many seconds this is, it gives you 0. So his velocity is 0 there. Okay. Now, you can just skip all this and just look straight at the velocity time graph. When you look at the velocity time graph, well, we're looking at average velocity. So his average velocity from 0 to 5 seconds. So 0, 1, 2, 3, 4, 5. Okay. His average velocity was 1.4, right? Yeah, 1.4. So his average velocity was basically that. Straight line. Okay? And then he had 1, 2, 3, 4, 5, 6 seconds of 0. So, boom. 1, 2, 3, 4, 5, 6. Draws all the way out here. And then he had a velocity of 2.3. So, 2, 3. Velocity there. Okay, boom, got it. So you could look, I did not mean to touch my board there. You could look at that and figure out constant velocity, 0 velocity, constant velocity. Boom. Okay, now usually there's acceleration as well. So his velocity doesn't change perfectly like that. Usually in this graph, there is some sort of acceleration, which means that he has to ramp up to that velocity. Okay, now for this one, the slope is our acceleration. Did I spell that wrong? Probably. Because remember, acceleration is velocity over time. So that's your slope. So if your velocity is a straight line, there is no acceleration. If your distance is a straight line, there's no velocity. You're looking at the different slopes of each one. Okay, so those are your different graphs. So when you have positive distance, you're going away from where you started. Negative distance means you're coming back to where you started. Positive velocity means you're going away from where you started. Negative velocity means you're going back to where you started. Okay, and then acceleration. Positive acceleration means you're getting faster. Negative acceleration means you are slowing down. That's basically what it comes down to. Okay? I just wrote slop instead of slope. Please forgive me. There you go, I fixed it. Okay, moving on. Good Lord, can't find. It's making me do so much cleaning up on the chat. Just type your questions and we won't have this much trouble. Okay. What is the formula for specific heat? Okay. Specific heat deals with the amount of heat added. So our formula is Q equals mc delta T. Q, m, c, delta T. Those are all our variables. This is heat. This is mass. This is specific heat. And this is our change in temp. Remember, anytime you see a delta is change. Okay, so change in temperature. Okay, so that's it. You're either going to be given the heat added, how much heat is added, how much heat leaves. That's your Q. This is in joules. Okay, that's in joules. You have your mass in kilograms. You have your specific heat, and you have your change in temperature, and that's degrees Celsius. And then this mass is usually given in grams or in kilograms, okay? And that changes based on your specific heat, okay? So specific heat, the unit, you just rearrange it, okay? So rearrange your formula. You have C is equal to Q over M delta T. You can find out your units for C based on your units for M, okay? Based on your units for Q, M, and delta T. Q is either in joules or calories. That's the other one, okay? Okay, so if this is in, let's look at our units. We have joules over grams degrees Celsius. Okay, that is our unit for specific heat. And that means it takes this many joules. Joules is energy. That's your Q, your heat. It takes this many joules to heat up 1 gram of whatever you're talking about by 1 degree Celsius. So if you have 1 gram of silver and you want to raise that silver's temperature by 1 degree, you have to put in heat. Okay, anytime you raise temperature, you have to put in heat. So if you put in a certain amount of heat to raise it exactly 1 degree Celsius, that is the heat needed. That's your specific heat. Okay, so it's the amount of energy, either in joules or calories, that is needed to raise 1 gram of it by 1 degree Celsius. We don't care about Fahrenheit, 1 degree Celsius. That's all specific heat is. Okay, so if you have a higher specific heat, like water has 4.184 joules per gram degree Celsius, if you have a higher specific heat, then your water, the substance you're talking about, takes more energy to raise in temperature. That's a good thing. That's called an insulator. Okay, if you want something to not get as hot as fast, you have it as an insulator. Okay, like styrofoam. You can put something warm in styrofoam and it will stay warm. Okay, it won't lose that much heat because the styrofoam takes so much energy, it takes so much energy to raise the styrofoam's temperature. Okay, now this is a bad thing if you want to cook. obviously you don't want to cook on styrofoam. It will never get hot enough. So metals, most of the time, metals, not every single metal, but most metals, the vast majority of them, have a very low specific heat. It does not take a lot of energy at all to heat them up. Remember, we did this with our spoons. Our spoons were the same exact temperature, but the metal feels colder because it takes less energy to heat up the metal. So it feels colder for you because it's taking your energy away and heating up the metal. Okay? Your energy is leaving your hand. We talked about that. We looked at these spoons sitting in a bath and which one's going to heat up fastest. Okay, they're both in the same hot water bath, but the metal one's going to heat up faster because it takes less energy to heat up the metal spoon. Okay, that is what specific heat is. Okay. Are all the formulas going to be on the test? No. That's just the way it is. Not all formulas are going to be on the test. You will get some formulas. Some of them will be helpful, but not all of them will be helpful. Let me see. You're going to get a formula sheet. Okay, and that formula sheet is going to have, it comes from the state of Georgia, and it has some formulas on it, but not all. Okay, so that's an issue. So if you're looking at the formula sheet and periodic table, physical science reference sheet, okay? You will get this reference sheet. Let me see if I can get it on the screen. You'll get this reference sheet right here. Okay, this is what you will get. Now, let's see, can I did not turn this around. Here's my clicker. I forgot how to, it's not gonna let me turn it. So you get, let's see, you get velocity is displacement over time, acceleration is final velocity minus initial velocity over time, weight equals mass times gravity, force equals mass times acceleration, work equals force times distance, mechanical advantage is effort distance over resistance distance, or resistance force over effort force. You get density, you don't need that yet. Okay, that's next semester, but you get it anyway. You get volume of rectangular solid, length times width times height. You get heat lost or heat gained, which is the Q equals mc delta T. And look, it says mass times specific heat capacity times change in temperature. So it writes out what each variable means. It says heat loss, that's your Q. Mass, that's your M. Specific heat, that's your C. Change in temp, that's your delta T. Then for waves, you get V equals IR. You get Kelvin equals Celsius plus 273. So if they give you something in Kelvin, or you can convert it to Celsius. You get acceleration due to gravity, which is roughly 10. You get a Newton. 1 Newton is equal to 1 kilogram by meter over second squared. And you get 1 joule is what's equal to Newton times meter. So those are the formulas you get. So you get formulas. They're not all going to be on there, but you do get these formulas that are on there. Okay. So those are the formulas you get. There you go. If an object stops, will it remain at the same spot and vice versa unless an outside force mess with it? Yeah, that's Newton's third law, you know. Or, sorry, first law, with inertia. Object at rest stays at rest unless an outside force acts upon it. Okay, So that's Newton's first law. What is frequency and how is it calculated? Okay, frequency is the amount of times your waves comes through. Okay, so it's the amount of times in 1 second that your wave goes through. Where did my other board go? Oh well. All right, other board. Let's see. Frequency of a wave. So you have your wave. Okay. It is a wave. Okay. So you have your middle line here. Okay, this is the best wave you've ever seen. I know. Okay, so right, we have our crest. We have our crest, which means from here all the way over here is our wavelength. Okay, so frequency. Measured in hertz, Hz, that's our unit. Okay, and it counts the number of times a full wavelength goes by. Okay, so it's from here to here, okay, to here, so on and so forth. Those are all the full wavelengths. Okay, so in 1 second, how many wavelengths? Okay, so in 1 second, this wave is moving. How many wavelengths are going to pass by it? That's what frequency is. Okay, so obviously if it has a smaller wavelength, you'll get more wavelengths coming through. So smaller wavelength usually is a increase in frequency. The faster it's moving, the more energy it has. Okay, so the higher your frequency, the higher your energy, because you're getting more wavelengths coming through in a shorter amount of time. Okay, so that's a higher energy. And then the other part is amplitude, right? The higher energy is, if it has a bigger amplitude, that's the other side of the energy coin. Okay, now when we're talking about sound, our frequency is our pitch. So if you have a lot of wavelengths coming through in 1 second, we hear that as a very high pitch. So the higher your pitch, the more frequency you have. The lower your pitch, the lower frequency you have. Okay, but that's only for sound. In other waves, it just deals with how many wavelengths pass by in 1 second. That's it. That's all frequency is. Okay, moving on. I'm not even looking at chat real time anymore. Just to warn you. How do you calculate frequency? Good question. Okay, this is number of wavelengths over seconds. So if you have 6 wavelengths in 3 seconds, so 6 wavelengths in 3 seconds, well then you have a frequency of 2 hertz. That's how you calculate it. Okay. Going into more detail of Newton's laws. No, I will not go into complete detail. First law. Object at rest stays at rest. Object in motion stays in motion. That deals with inertia. The more mass you have, the harder it is to move something. Think about it. It's easier to move a toy car that's sitting on a table than a real car sitting out in your garage. Okay, so if you have to push both of them, it's going to take more of an outside force to push the bigger car because it has more mass, therefore more inertia. The more inertia it has, the harder it is to get it moving, or vice versa, the harder it is to stop it. Okay, you can stop a Hot Wheels car with your finger. You cannot stop a real car with your finger. Okay, it's just not going to happen. You will lose that finger. Okay. Second law, F equals ma. The more net force you have, the faster acceleration you have. If you have no net force, you have no acceleration. Okay, that's what F equals ma. That's the second law. Third law: every action has an equal and opposite reaction. If you punch a wall, the wall punches you back. If you're hitting a baseball, the baseball's hitting the bat back. If you are driving and you hit an insect, well, the insect hit your car back at the same amount of force at the same exact time. It's just in the opposite direction. Equal and opposite reaction. Okay, those are the three laws. Okay. What happens to the speed and frequency of a wave when it passes through air and then glass? Okay, so based on what it's traveling through, it determines the speed. So if it can travel faster through something, then it's faster. But it travels fastest through. Well, let's talk about light. Okay, so light travels fastest through a vacuum. Travels second fastest through the atmosphere, and then through water. It's a thing. So here we have our water. Here we have our fish in the water, just chilling. Okay, we have our light coming down. It's going to hit this water. Okay, when it hits this water, it is traveling at a certain speed in the air. So theoretically, you would think that it would just keep going on the same exact line that it came in on. But that's not what it does. Some of the light goes up, and this is reflection. Reflection. And then some of it actually bends, because it's either going faster or slower. So it bends either this way. Well, that's too big of a bend. It doesn't bend that big. Okay? It either bends going this way, or it can bend going this way, or it can bend a little bit. As long as it's bent, okay, this is our refraction. Now, based on the two different mediums, it determines how it is bent, and you can actually mathematically calculate where exactly that light ray is going to bend and what exactly it's going to hit. Now, this light ray will never ever hit this fish because it cannot bend backwards. Okay, it can't bend backwards. That will never happen. But theoretically, it could bend and hit that one, depending on the index of refraction for each medium. Now, we don't have to calculate that. So all you have to know is that it changes speed once it enters a new medium. And since it changes speed, it then bends. Okay, so it bends. That's called refraction due to the different speed of the mediums. Now, electromagnetic waves do not need mediums, so they travel the fastest in a vacuum, but they also do travel through mediums, and the denser the medium, the slower it goes. That's a good way to remember it. So water is far more denser than air because it's a liquid, and air is a gas, so it travels slower through the water than it does the air, therefore it bends, and it's called refraction. Okay. Frequency of light never changes. Okay. I don't know why you said that. The frequency of light does change. That determines what color of light it is, by the way. Violet light has higher frequency than red light. Red light has very, very low frequency. Violet has higher. And then light, electromagnetic waves, gets into light that you can't even see. Ultraviolet has a higher frequency than violet. Gamma has the highest frequency. Radio waves have the lowest frequency. Okay, remember, it's that huge spectrum of electromagnetic radiation. Visible light is just a very tiny portion of that spectrum. Okay, and that spectrum is determined by the wavelength and the frequency. So that's it. Does he have a bookshelf? Akino, you don't know what a bookshelf looks like, dude? Like, you obviously can't tell that that's a bookshelf? Okay. Acid wave. Can you explain electromagnetic induction, or whatever happens in generators and the conversion of energy from mechanical to electrical? Yeah. Yeah, so when you're looking at electromagnets, okay, electromagnetic, you have electricity, you have magnetism, and it goes back and forth. If you have electricity, you create magnetism. If you have magnetism, you can create electricity. So if you change your magnetic field, okay, you go back and forth, you switch directions of your magnetic field really quickly, okay, you will induce a current in a wire, okay, and that current will then be electricity, okay? Remember, solenoids are the opposite. They are current going through a coil, which creates magnetism, a magnetic field, okay? Whatever happens in generators. So generators take mechanical energy, the energy of motion. Mechanical energy is potential and kinetic energy combined, okay? It takes the mechanical energy and it spins a turbine, and inside that turbine it's set up that the spinning of the turbine has the magnet that it's rotating around, okay, and it's flipping the magnetic field back and forth, which is inducing a current, and that current is considered electricity because it is. Electricity is current. And so you're spinning that turbine with mechanical energy, and it is inducing a current, so you are transforming your mechanical energy into electrical energy. That's how we make electricity. Now, you can use multiple different things to make that electricity happen. You can physically turn the turbine, like if you have a bike that produces electricity. You can have a dam with hydropower. You can have burning of coal or something in the hot air. You heat up water, and the water steam turns the turbine, so on and so forth. But you take that electricity and you can convert it into mechanical to spin the turbine, and then you take that mechanical energy and you convert it into electricity. That's a generator. Generators generate electricity. That's the whole point. Okay, keep going. Can you explain why crossing the x-axis in velocity time graph shows a change in direction? Yeah, so remember, velocity time graph. Okay, I don't know what happened to my my stuff. I had all this built out, and then I put in the formula sheet, and I got rid of all of it. Okay, but your velocity time graph has direction. Velocity is a vector quantity. Okay, so a vector quantity means it has direction. If you go one direction, then you have to show which direction you're going, and if you're going the other direction, you show the other way. Okay, and that is your velocity. Okay, and if you cross the x-axis, that means you passed home and you keep going the other direction. Okay, change of direction. A positive velocity means you're traveling one way. Negative velocity means you're traveling the opposite direction. That's all it means. Okay. What is Faraday's law in electromagnetic induction? Okay, you guys need to go review that because multiple people have asked about that. You need to go look in your notes. There's a whole note that we did of fill in the blank notes. There are those for the PowerPoints are on eClass, and you can go review all that. You definitely need to know that. Okay. Displacement and distance. Yeah, that's easy. Displacement and distance. Okay, displacement. So, let's say you start here. You travel this way, you travel up, you travel this way, you travel up, you stop here. Okay, so if you start here and finish here, the route you actually traveled, you only traveled this far. That's your displacement. Okay, but everything in black is your distance. So distance is the amount you actually travel, like all of this. Okay, you actually traveled that, so that's your distance. Displacement is how far away from where you started. So that is your displacement. That's the difference. So if you are looking at how far you actually travel, that's your distance. You count up how far you actually travel. You add all that together. If you're looking for how far you actually moved, that's your displacement, right? So you wake up in your bed, you travel all day, but you end up in your bed. So ultimately, you didn't go anywhere by the end of the day. You ended up exactly back in your bed. Your displacement was 0. You ended up exactly where you started. But your distance added up throughout the day. You did travel a bunch of places, but your ending point was exactly the same as your starting point, so therefore we say your displacement was 0, even though your distance actually is a number. Okay? What happens to frequency and the speed of electromagnetic wave as it passes from air into glass, and why? That's the refraction. Okay, it moves slower in a more dense material, so therefore it bends. Okay, that's the speed of the electromagnetic waves. The frequency does not change. What is you gone? Like, seriously, January memes? Really? Keep going. How do you know when to use slope and when to use a graph? Well, if they give you a graph, you gotta use it. That's basically how. If they give you a graph, you should always use the graph. So if they give you the graph, there's always going to be information you can get from the graph. If it's a distance time, your slope gives you your velocity. Your distance gives you how far away you are. You can always find your displacement based on the starting and the ending distance. Your velocity time graph gives you the speed that they're moving. It also gives you direction if it's velocity, because direction is a vector. So if it's positive, they're moving away. If it's negative, they're coming back. Okay, how do you know when to use slope? And then velocity, you can find the acceleration, change the velocity over time, acceleration. Okay, so you gotta all do that. Okay. Um. Lots of nothing in the chat. Thank you for dirtying up the chat. I'm very, very glad that I'm spending time reading nothingness instead of helping you. Explain the Doppler effect? Yeah, it's that's the Doppler effect. There you go. How do you know if it's displacement chart or just an XY graph? I don't know what just an XY graph is. Every graph is an XY graph. You have an X-axis and a Y-axis. I don't know what that means. Doppler effect again, guys. If it's the Doppler effect, you have that perceived higher pitch because the waves are hitting you at different the waves are compressing and hitting you, and then as you go away, it's perceived lower pitch because the waves are more spaced out. Okay, so since the waves are more spaced out, it's a perceived lower frequency, so therefore it's a perceived lower pitch. Okay, it's the opposite of it coming toward you. As it comes towards you, it's a perceived higher frequency because the waves hit you, they compress and hit you faster. So then you hear it as a higher pitch. Ooh, good question. One finally. Got to get through all the crap in chat to finally get a good question. All right, let's look at this. What is going on with the energy in a phase change diagram? So, phase change diagram, heating curve. That's green. I wanted black. Heating curve. Here we go. Here is our heating curve. Okay. We have our time. We have our energy. Okay. As you go up, okay, the heating curve looks like this. Plateaus. It plateaus and it goes up again. This is our heating curve. Okay. Here's our energy. Energy. We are adding energy. This is our Q. Okay. Variable Q. Okay. We are adding energy. Okay. We can also look at it as our temperature. Okay, so the vast majority of them you will find temperature. This is our degrees Celsius. Okay, you can see it both ways. Okay, you will most likely see temperature on the x-axis, but they have been known to give you an energy one instead. Okay, and so let's look here. I'm not going to label them because what's important is what's happening to your energy here. So as you heat up, okay, as you heat up, the energy you add in here and the temperature here as you heat up, as you add energy. So this entire time, right? We're moving this direction. That means we're adding energy. So our energy is getting larger, and as you go up here, you are increasing temperature. Okay, this is very important that you read the graph correctly. So as you move across, you're adding energy. As you're moving up, you're increasing temperature. So these sections right here are weird, because we're adding energy, but we're not increasing temperature. And remember, temperature is nothing more is your average kinetic energy. So if our energy is being increased, but our temperature stays the same, that means we are not increasing our kinetic energy. That means we must be increasing our potential energy. So here our temperature goes up. That's an increase in kinetic energy. Here, this is potential energy. Here it's kinetic energy. Here's potential energy. And here's kinetic energy. Okay? Every time you're increasing your potential energy, this is a phase change. Okay? So when you increase your potential energy, that's a phase change. So this one obviously is going to be melting. This one is boiling or vaporization. Okay? And then we have our states of matter. I'm out of colors. We have our states of matter here. Okay? So this is our solid. This is our liquid. This is our gas. Okay, so anytime you have a positive slope, that's your state of matter. Anytime it plateaus, that is a phase change. And you go state of matter, solid, phase change into a liquid, phase change into a gas. Now to phase change, you have to put in energy. But the energy you're putting in doesn't increase the temperature. So that means the energy you're putting in is potential energy, not kinetic energy, because kinetic energy is temperature, basically. Average kinetic energy is temperature. So you can use these graphs to tell what's going on with your energies just based on looking at temperature. If temperature is increasing, your kinetic energy is increasing. If temperature is decreasing, your kinetic energy is decreasing. If it stays the same and yet our energy is still adding or being taken away, that means our potential energy is changing. Okay? That's what that means. Good question. Alright, seriously, it's really hard to find the questions because you guys are so concerned with making fun of each other. Just chill. Okay, let's look at net force. So the easiest way to do net force. Okay, the easiest way. Look. We've got basically a tug of war. So we got Steve over here. And we've got Bob over here. Okay, and they have a green rope between them. Steve is trying to pull this way. I didn't want that in green. Steve is trying to pull this way. Bob is trying to pull this way. Okay? If Steve pulls with a very large force and Bob pulls with a small force, well, think of it in your head. Who is going to win? If you have a tug of war, Steve with a very large pull, Bob with a very small pull, obviously the winner will be Steve. So our net force goes in Steve's direction. to the left. The larger force wins. Okay, now that's the way I think about every single force pair that I look at. So if they give you a box, and that box has forces acting on it, so obviously it's got force gravity, and if it's sitting on a table, it has normal force. Okay, now the way that you know that no one wins that tug of war is that box isn't moving. It's sitting on the table. So F grav is equal to Fn. So your net force is basically the normal minus gravity, but they're equal, so it's 0. So F net is equal to 0. Okay? No one wins that tug of war. It's essentially like those forces are not there because they cancel each other out. But if I push this box, I have force applied, and it moves a little bit, I'm going to have a smaller force friction. Now, who wins this one? Applied has a larger arrow than friction does, so my net force is going to go to the right. Okay? The net force is going to be smaller than the applied force because you have to subtract friction from it. Okay, we have friction acting on it in the opposite direction, so therefore our applied force is smaller than what it would be if it did not have any friction. Okay, so our net force is to the right. That's important because we have F net is equal to our mass times acceleration. If we know the mass of this box, we can easily find the acceleration caused by that applied force. That's where it becomes important. Okay, so to find net force, you add up all the forces, the sum of all the forces. These two forces cancel each other out. The right and left force do not cancel each other out. Okay, the applied force is larger, so therefore it has a net force going to the right. And if these were labeled with the amount of newtons that the forces were, you could plug in and find your acceleration. That's net force, your force pairs. Okay, unbalanced force leads to acceleration. Okay, what is interference? It's when waves combine. If two waves interfere, so if you have one wave like this, okay, and you have another wave that's exactly the same, and they were to hit each other, okay, these waves would combine. When this wave goes up, this wave goes up, and you get a resultant wave of a much bigger one. Okay? They combine. Think of it like a trampoline. If you've ever been on trampoline, if you've noticed when you're bouncing, sometimes if you and a friend are bouncing on a trampoline, you bounce he bounces right before you, you get launched into the air. Okay, that's basically what's happening. Okay, so they combine, your bounce and his bounce, or these waves, the two crests combine, and it results in a much bigger wave. Now, the opposite can be true. If you have a wave like this, and then you have an opposite wave like this, when these combine, they cancel each other out, and you're left with nothing. Okay, and that is how noise-canceling headphones work. If you have a noise-canceling headphone, you can turn it on. Okay, it usually requires a small little battery. You can turn on the noise-canceling headphone, and all of a sudden, all the sounds go away. Well, that's because the noise-canceling headphone is detecting the sound that's coming in, and it's hitting it with a wave that is opposite of it. Therefore, it's canceling out the sound wave, so you don't hear anything. That's how noise-canceling headphones work. It's called destructive interference. Okay, so destructive results in them canceling each other out. Constructive results in them really adding to each other and resulting in a big one. Now, this can be the same as a force pair, right? In the sense that you could have one that's really big, okay, and you can have one that's quite small, and it will still result, okay, these will cancel each other out, but it will still result in just a smaller wave, right? Because they cancel each other out. It's not as tall, but this one still kind of wins, so you have just a softer or a smaller amplitude wave as the resultant. Okay, that's interference. You have constructive, you have destructive, and depending on where they are is depending on if they're both going in the same direction, it's constructive. If they're going different directions, it's destructive. What is the difference between convection and conduction? Well, there's 3 types of heat transfer. Okay, convection, conduction, radiation. Okay, now remember, conduction, touching. Convection, flow. Radiation, okay? Radiation, think of it like sunlight. Or no touch. Okay? So, that's how I think about it. Conduction, that's the easiest one. You touch a hot pan, it's hot, you get heat. Conduction, you touch it. Okay? Convection, a little harder. Think of it like water. Okay? You heat up the bottom of the water. This is where you get your convection current. Remember, you heat up, you become less dense, you rise, you are away from the heat source, so you cool down, you become more dense, you sink. You hit the heat source, you become less dense, and you rise, you become more dense as you cool off, and you sink, and you create this nice little current, okay? You get a nice little convection current, okay? I put that next to conduction. It was supposed to go next to convection. Okay, now think of this with fluids. So fluids include liquids and gases. Okay, so it flows. This is how a hot air balloon works. This is how you boil water, how water boils, and how it's all the same temperature as it's boiling because you have convection. You have a flow of the actual molecules. Conduction, you touch a hot molecule, it transfers its energy to you through actual touching. Radiation is like sunlight. It travels without touching and without flowing of the actual molecules. It travels as energy, and so you can feel it. You can feel this from a fire. You can feel it from just a really hot light bulb. You can feel this from the sun. Okay, that's radiation. Okay, and it's like if you can feel it without it touching and without the airflow carrying the currents. So convection is basically weather, okay, and like boiling water, hot air balloons, even a pool. Okay, conduction is touching, radiation is sun or fire. That's how I remember all of them. Okay. What is rarefaction? That deals with your mechanical waves. Okay, so your longitudinal waves. So if you have a longitudinal wave, you have your compression, and then it kind of spreads out, and then you have another compression, and kind of spreads out, and you have another compression. Okay, this is your wave, it's just longitudinal, right? The motion of the particles is parallel to the motion of the wave. So here we have our compression. And then here we have our rarefaction. This is for longitudinal wave, similar to what a crest and a trough is for a transverse wave. Okay, that's what rarefaction is. Electric motor, that's electrical energy to mechanical. Think about it like an electric scooter. It spins the wheels for you. Okay, so it's taking the energy from the battery, the electrical energy, spins the wheels for you, and you move. That's mechanical. Mechanical is the addition of potential and kinetic. Okay, it's the energy of movement. So electric motor, think about what a motor does. A motor pushes you forward, it moves the wheels. Therefore, a motor is ending in mechanical energy, so it starts in electric, and that's an electric motor. Okay, it's the opposite of the generator, whereas generator ends in electricity, but it starts with mechanical. Atomic domain and magnetic domain mean? Okay, so when you look at a magnet, it has very small little atoms, right? And if the atoms have a domain, which way their magnetic field point, and if all the atomic domains line up, therefore you get a magnet. If they all are pointing in completely different directions, you do not have a magnet. So you can make a magnet from like a nail. If you have a magnet and a nail, you can rub the nail over the magnet, and then you've aligned all the atomic domains on the nail, and it acts as a magnet for a small amount of time. Okay, that's what the domains are, and they're in the notes where we drew the arrows in the small little parts of the bar graph, or the bar magnet, and when they all line up, that's when it is a magnet. If they are not lined up, if most of them are pointing in complete different directions of each other, it is not magnetic, and it will not have a cohesive magnetic field. All right, so in Doppler effect, does it only change the direction? Doppler effect doesn't change the direction. Doppler effect deals with a perceived. Your brain is stupid. Okay, that's what Doppler effect is. It's your brain being stupid. So if you stand here, okay, and we have an airplane here, okay, and he's flying this way. He's putting off sound waves, right? Sound waves. And those sound waves look kind of like this as it travels towards you. So if that airplane stayed exactly where he was, the sound waves would come and you would hear the plane exactly like that. Unfortunately, the plane is moving. Okay, so since the plane is moving, a sound wave is coming here, but now he moved a little bit, and now he's over here. So now he's got these sound waves, and they're coming. Well, now he moved again. Now he's over here. This plane keeps moving, and now he's got these sound waves, and they're still moving. Okay, now it's getting messy, right? Now you got all these sound waves that are traveling, okay, and this sound wave is traveling kind of at the same. So you as a person, as a bystander, your ear and your brain are going to hear not just the sound waves from when the plane was at this location, but also the sound waves here, 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 all the way, okay? Those sound waves are going to keep coming, okay? Now, when he's traveling towards you, these sound waves are going to bunch up. Okay, when they bunch up, you're going to get more waves in a shorter amount of time. And your brain goes, wait a minute. When I get more waves in a shorter amount of time, that means it has a higher frequency. And when I have a higher frequency, it's a higher pitch. So you're going to hear it as a higher pitch. So as it moves towards you, it's going to get louder, and the pitch is going to be higher. As it moves away from you, the opposite is true. Instead, you'll get these waves, and then you'll get these waves, and then you'll get these waves, and then you'll get these waves, okay, and the waves will come much, much slower, okay, and they're going to be drawn out, okay, and it's all because the plane is moving away from you. So as the waves are drawn out, your brain goes, wait a minute, I'm not getting as many waves anymore in my ear, therefore the frequency must be lower. Then lower frequency means that it is a lower pitch. So that's why when something fast goes by, like a car, it goes meow. Okay, and it speeds up, it gets a higher pitch, meow. And then as it passes you, it slows down, or the pitch slows down in your brain. Okay, the car, if you're sitting in the car sounds the same the entire time. But to someone you drive by, it sounds like a little different. Every time you hear a car goes by, you're used to it kind of going by, it's like meow, meow. But when you're in a car, you never hear that, because in the car it's not moving. You're moving with the car. You hear the constant sound. It's no different. But when you're standing and the plane or the car passes you, it bunches up the sound waves coming in, and therefore your brain's like, haha, I know what to do. And it hears it as a higher pitch, and then as it goes away, your brain's like, I'm still very smart, and it hears it as a lower pitch, even though the sound never actually changed. Okay, so that's the Doppler effect. How do you calculate the resistance of a parallel circuit? 1 over R1 plus 1 over R2 plus 1 over R3, so on and so forth, equals 1 over R total. So therefore, you do 1 over R for every single one, you add them up, then you take the reciprocal of your answer, and you get the total resistance. Okay, I highly doubt you'll have to do that, but that's how you do it. How do you find the total resistance of a series circuit? Well, you just add them all up. Resistance 1 plus resistance 2 plus resistor 3. Add them all up, you get the total resistance. Alright, last call. Then you guys got to go to bed because you have 2 finals tomorrow. You have to make sure that you are well rested. You're well rested. So how would you solve resistance in a graph? What do you mean? What graph? So that the graph, the resistance is your slope. So if it has a very high slope, then it has high resistance. If it has a less shallow slope, it has lower resistance. Okay. So that's if your voltage is your y-axis, that's the case. But you asked the opposite. You asked x-axis is current, y-axis is voltage. No, that's what I said. If your y-axis is voltage, then it's the slope. It's the change. Rise over run, dude. Rise over run. Take y2 minus y1 over x2 minus x1. Rise over run. How far does it go up? How far does it go over? That's all you do. That's slope. How do you find the resistance and current of a parallel circuit? Okay, parallel circuit, the resistance is 1 over R1 plus 1 over R2 plus 1 over R3, so on and so forth. Okay? So you have to take the reciprocal of it. So 1 over R total equal to 1 over R1 plus 1 over R2 plus 1 over R3. So on and so forth. However many resistors you have, okay, you take the resistance of resistor 1, resistance of resistor 2. This is for parallel. I don't even know how to spell parallel. One R, two L's, parallel. Okay, and then a series. You have R total is equal to R1 plus R2 plus R3. Now remember, some circuits can have parallel parts and series parts, so you might have to use both of these on the same circuit, depending on what branch you're looking at. How do you find the current? Well, you do V equals IR. So you change it around. So, yeah, V equals IR. You change it around to I is equal to V over R. And you plug in your V. and you plug in your R. Now you can find your R using this. So R total comes all the way down, and you plug it in there. Then you have the voltage that of the battery you're given. You can find your current. Okay. Is a fan open or closed system? What do you mean? What do you mean by a fan? Like blowing air? It's taking the electrical energy that you plug it in, and it's turning it into mechanical energy of the blades moving. Technically, the blades are encountering air resistance. The air resistance is resulting in some of the electrical energy to be converted into thermal energy instead of the mechanical, so you could classify it as an open system. Alright, we are calling it. You need to do your last minute stuff, and then you need to go to bed because you have 2 tests. Do not show up tired. That is worse than anything you could potentially do. You must show up well rested, eat your breakfast, okay? You don't want to be hungry during the test, and you need to be rested so your brain could work. Your brain does not work well when it is not rested, okay? So you must get some sleep. So we are calling this here, and we are looking through there. Sod, you know the answer. Terminal velocity is when you have 0 net force. If you have 0 net force, you have 0 acceleration. Okay, your air resistance is equal to the gravity, 0 net force, 0 acceleration. Alright, and with that, good luck tomorrow on your finals, and get some sleep.